Okay, good morning, students. Today is August 19th, okay? Today, we complete the 13th week of class, so we have only one left, okay? I'm going to answer or try to give you a short explanation of some of these details about this, the use of this program, shared stress for multi-cells. Okay, and there was some error that I just corrected. So it's not a big thing, but there was an error. So I corrected that. So I posted a new version of the material, okay, for this last part of the class. For you to have a general idea, okay, I don't think we're going to complete the material that we have for this session. So we're going to go with that on Tuesday. And from that point, I'm going to discuss or describe some formulations from the classification society, okay? So you can start seeing the relationship between the structural mechanics analysis that we have presented in this class, beam theory, effective breadth, plate bending, and all of that. They are connected with some of the relations that the classification, at least one classification society presents in his rules. Okay, so I would like you to pay attention to that. And there is a last subchapter, which is going to be just described at the end of the next week. So probably we're just fine with the material, okay? And probably the last Friday from today in a week, I would like to do some sort of evaluation of the class. So please come this session, okay? We're going to go back to Spanish, and I would like you to tell me some feedback. So we will be able to improve for the next year. Okay, so this is that. Can you see my white screen, people? Can you see my white screen?
Yeah, doctor.
Okay, so we are we're trying to analyze a section, whole section like this, and it has double bottom, and it has one longitudinal bulkhead, right? Okay, so the first question that we need to answer is how many cuts do we need, okay, in order to analyze this section, okay? So okay, now let's see how far can we go, okay? I'm going to include with the cuts. So let's do a cut here and another cut here, okay? So we can go on, okay? Let's do each one of the path. I'm going to use a different color, okay? So let's start with yellow. So we will go like this, and we can go up to here, okay? Since this is symmetric, I'm going to use the same color on the other side. That's 2. But here, we have a connection, so we do not know how much of this shear flow goes in this and in that direction. So we have to stop there, okay? Now, that means that we could include another cut here and here. If we do that, in that case, we could go on with this path up to here. Similarly, from the other side, we could go in this way, like this. So this path includes deck, half deck, this side, full side, because we have a cut here. So this This vertical side could be considered, and finally, the half of the bottom. Similarly for the other side. Now, for the vertical element, okay, for the vertical element, since we can start here, let me change color, let's do this. So we could go from here, and we can stop here. We have to stop here. We can go from here, we have to stop here. I'm sorry, this is the same, sorry. Sorry. That's the next, and here, again, we have a jump, so we cannot do anything else. So we can start here. Okay, we can start here, and we can use this and that. Are we complete, people? Are we complete? Are we complete? No, no, because we still need to include this part here is not included. So we still need another cut. If we want, we could do a cut here. And we could describe the last path like that. And so how many paths do we have, Miss Valdez? How many paths do we have?
Four cuts.
We have two yellows, two greens, that's 4, one orange, that's 5, and this I don't know what, this pink. We will have 6 paths. Do you see the 6 paths? Not 6 pack, 6 path. TH. People, do you see the 6 pack? 6 paths. See the 6 paths? People, do you see it? Okay, I'm going to see this is path 1. This is path 2. Let me change color. This would be path 3. This would be path 4. Okay. This, the orange, this would be 5. Finally, the pink would be the path 6. Okay. Miss Leon, Caroline Leon, how many cells do we have? How many cells do we have in this case, Miss Leon?
We have 5.
Cells. How many cells do we have?
4.
Mr.
4.
Zurita? 4. Yeah, 4. So we have, remember, this direction is positive, this direction is positive, this direction is positive, and this direction is positive. So this is going to be cell 1, cell 2. If you want, this is cell 3, and this is cell 4. There. Okay. So let's do the example in cell 1. Cell 1. Okay, cell 1 is formed by this path. This is path 1, only up to here. Path 1 continues up to here. See, if you want to make a cut here, you can consider this sector. You calculate the area, distance to the neutral axis, and you can calculate large Q, the first moment. And you can do cuts along this path up to here, and you can calculate the distribution of the shear flow completely. Okay, but for the cell 1, this is all what we need up to here. Now, on the right-hand side, we have the path 5. Path 5. And finally, here you have path 3. So these 3 parts of the path 1, the path 5, and path 3, they form cell 1. Let me put the name of the cell in the central part. So I'm going to this cell 1. Now, the key here is that we have to consider the signs. Okay? Now, let's do this. Mr. Chin Chin, the path 5 will have sign positive or negative. The path 5. The sign for the path 5 will be positive or negative.
Positive.
Remember, what we're doing right now is take parts of each one of these paths and try to form the cell. The cell 1 is like that. We have 3 pieces of the path. Now, path 5, is it positive or negative, Mr. Chin Chin?
Positive.
Pardon me? Didn't get it? Positive or negative?
Positive.
It's positive. Are you sure? Ms. Santos, do you agree with Mr. Chin Chin that path 5 is positive?
Yes, doctor.
Yes, because you see that in this area, this is coming downwards. And this is also coming downwards. So this is positive. Okay, Mr. Mendez, how about path 3 and 1? Mr. Mendez, path 1 and 3, are they positive or negative?
And negative.
Negative, yes, negative, because you see that in this part here, the positive goes like that to the left. And the path 3 in this part goes to the right. So the contribution is going to be negative, and the contribution for that is also going to be negative. Questions so far, people? Any questions so far?
Doctor,
No
the
questions?
paths have to have the same thickness?
Not necessarily. Not necessarily. Remember that when we define each path, let me use this. Where is my this? For example, let's suppose I'm going to define the path 1. Okay? I have this point here, and probably that point will be y equal to 0, and the z is going to be equal to the depth. All right. We're going to put another point here, and another point here, and go on. I'm not going to do the whole thing. So if you had, for example, maybe you have seen some plants. Maybe I could try to bring some material for Tuesday. And you will see that in this area, usually the thickness of the plating increases. Why is that? Well, in part it's because in this part here, see, since you are away from neutral axis, normal stresses are high. And the shear stresses, remember that on the sides, are very important. They have decreased a little bit from neutral axis. When you go up, they decrease a little bit. But still, on the side, they are still important. So in the connection between the deck and the side, in this area, in general, both are important. Normal and shear. And then you have to combine. So as a result, in this area, usually you put a little bit more of thickness. So is this were the case, okay? In that case, Where is my pointer? Where is my pointer? There it is. So this is my point one. This is my point one of the path one. This is the point two, okay, of the path one. Now, if this thickness from here to here had a certain value, that value is going to be associated with the point two. And then we specify point three. If the thickness is the same, then the thickness at this point is going to be equal to the thickness at that point. In a real ship, okay, I'm sure, okay, in this part here, the thickness is going to be a little bit larger than in this part. So the value associated with, or the thickness associated with 0.4 is going to be a little bit larger than the values at 0.2 and 0.3. Ms. Santos? So you could include this variation in thickness when you define each one of the paths.
So if the thickness is larger on the deck, I select the thickness of the deck.
Yeah, what you can do, okay, hold your question for a second, okay? And then I'm going to change slide. But now I need to complete the data file, okay? Because this is, the first step is to define the paths with the artificial cuts. That's what we did on the left. The next step is to define each one of the cells. That's what we have done here on the right. But remember that we also have a Q2 in cell 2, and we have Q4 on cell 4. And those shear flows are going to influence the distribution of the shear flow of the cell 1, because these two cells are adjacent to the cell 1 which we are analyzing. Okay? So we still need a little bit more of information. Okay, now, let me change color here. Let's go to, for example, green. Okay, so here, I'm going to go with green. This is the cell 2. And down here, this is going to be cell. We see that in this path, okay, going down, the influence of cell 2 goes up because you go like that. So you need to include this path to define C1, but you need to tell the program, okay, that you have an adjacent cell, cell 2, that you share the path 5, and since the path 5 goes downward and the cell 2 then in this part goes upward, this P5 has to be considered as negative. Okay? Are you with me, people? Are you with me? See? So you have to do, first, you have to include cuts, define paths. Then you have to form pieces of this path to form the cell. Then you have to tell, if you have adjacent cells, okay, how they are going to contribute to the one that we are calculating. Okay. Are you with me, people? Okay, similarly, for C4, since you are going like that, okay, like that, in this path, it's going to contribute with the negative sign also. So P3 is going to contribute with negative sign of the influence of C4 over C1. Okay, see, all what you're doing on the right-hand side is you are forming equations. Okay, you are forming the equations. And in this case, for the first equation, you're going to have Q1, Q2, and Q4. Q1 is going to be formed by these three pieces. The contribution from Q2 is going to be negative, similarly for the contribution of Q4. And on the right-hand side, internally, the program calculates the Q1 star. Okay, Q1 star. And that's the first equation. And then go to the second equation for Q2, Q3, and Q4. So he has 4 equations, solve it, and finds Q1, 2, 3, and 4, etc. Ms. Valdez, this explanation help to you?
Yes, doctor. It's
Okay.
more clear.
Anything else? And anything else? I hope with this you can go on with the completing the solution of the assignment. Okay. Okay, let me go now to the question from Miss Santos. Okay. Okay. Suppose that let me change color because I don't like green. Shoot. Where's my pointer? Disappear. Oh, here it is. So let's suppose that we want to define, as before, okay, we want to define path 1. So here I have this, I have the side here, but now let's suppose that here we have larger thickness, like that. Here we have larger thickness and then we decrease. This is the distribution of the real thickness of your section. So what do we do in this case, Ms. Santos? Okay, we assume that here we have a cut. Okay, this is a longitudinal bulkhead. So we have 1 point here. This is my point 1. I could include another point here. It's going to be my point 2. I need to set the change in thickness. So I need a point 3 here. Could be a good idea, since we have this jump, to include another point here. And finally, we end up in here. We go downward, we could include another point here. In the jump, we need a change, another point, and then we go point 8. So to define this path, okay, this is the path that we are defining. Okay, we need point 1. So we said Y1, Z1, and the first value, the first thickness, basically doesn't work. Because what you do is you consider 1 point and go back to the previous one. Since this is the first one, there's no previous, so that value doesn't care. But if you want, you still have to do it. Then you specify the position of point 2, this one here. Okay, you get Y2, Z2, and you get the same thickness. 3, going to be Y3, Z3, and same thickness in this area. So the value of the thickness is the same. Then comes the change. In point 4, okay, from here to here, the thickness has changed. So you go Y4, Z4, and the thickness is a new value. So here you have thickness T2, here you have thickness T1, and since you are specifying here T2, yeah, considers that the thickness from this point and up to the previous one in this sector, the thickness is T2. Santos, in this way you can specify any change in thickness that you need.
Okay.
Okay. Actually, in this area, call it traca de cinta. And usually when you see the shell expansion, you see that there is some thickness, for example, on the side. And then the highest track, okay, and the top of the side in connection with the deck, that track usually has larger thickness. Similarly, on the deck, the first track in the deck has larger thickness. If the ship is very small, yeah, it's uniform. But in general, larger ships, yeah, they notice that difference. Because as I said before, on the top of the side, normal stresses are high, and also in that point, the shear stresses are also important. So you have to combine the two. And that will give you something that we're going to discuss either today or on Tuesday. Okay, people, is there anything else about this? Any other questions about this? In the definition of the tracks, my suggestion is do not include, for example, especially on the sides, don't include simply 2 points. Because internally, what it does, the program, is it starts doing these integrals to calculate the first moment. All of these calculations are performed numerically, right? So especially on the sides, right, the variation is not linear. If you put 1 point up and 1 point down, okay, so basically you are going to do is a linear interpolation. So the integration will be poor. So especially on the side, try to have at least 1 point at each end and at least 1 intermediate point. So you can describe curvature of the distribution in a better way. If you include at least 2 points on the side and also on the double bottom, that would be better. You will see that the distribution has some curvature, and that's could be well integrated. Okay, if there are no questions, then I'm going to switch terms, and now I'm going to go back to the material.
Doctor, I have a question about the for question for problem. The program. My parents, we have a problem because we don't use the program. We don't know use the program.
I'm sorry, you don't use the program? How are you going to calculate the shear stress distribution in this section? The idea is that you have this short experience of how to use this calculation, and you can go, if you doubt, what you can do is take a look, okay, in the appendix of the ABS rules. And they describe a procedure to calculate the shear stress distribution when you have longitudinal bulkheads. Take a quick look at that, and then you can tell me if that has some relationship with this procedure. I'm not going to tell you the answer. Take a quick look at that, then start thinking about what you have done here and see if there is any relationship. So all what I need is to have a first experience of calculating this, but I understand that you don't have the time to develop your own program. That's why I'm allowing you to use mine. Mr. Pesantes?
Okay, doctor. Thank you.
No problem, no problem. Okay, let me go. Where am I? So. See my screen, full screen or half screen, people?
Full screen.
Can you see my full screen or half screen?
No, yet, not yet.
No?
No full screen.
Full screen or half screen?
I'll screen.
Half screen. Okay, let's see. How about now?
There is screen.
Full screen. Okay, good. Let's see if I can, so I can see you. Your faces. I need to see your faces. Jesus Christ, superstar. Okay, so this is something that we studied last session. We're saying that the tertiary component of the stress distribution considers just one single plate panel. So we can apply plate theory, chapter 4, and the easiest model that we could use is to consider that all the edges, all the borders of the plate panel are clamped. Now, in yellow, we discussed that you have to accept that it's not completely correct. Why not? Because you think of, you have an stiffener, you have the plate, you apply the pressure, and this deforms. Once it deforms, okay, it is not clamped anymore. Yeah, but if you see that, when it bends like that, the stiffener rotates a little bit. So allows you also to include this redistribution of the bending moment because the slope is not zero. Okay, so we can use some of these relations or some of these relations from Timoshenko, but just as a general reference, and we will discuss this morning. Okay, so this is this Timoshenko solution. Here, this is the basic equation that we have for okay, from chapter 4. Okay, and we can use this for analysis. And we can use this table from Timoshenko or any other table that's similar in order to estimate the bending moment. With the bending moment and the thickness, we could calculate the stress. And this is cases when you do analysis of a system. If you want to do design, in that case, what you do is you need to determine the thickness, you know the pressure, and you have to select an allowable value for the stress. So 235, say, I cannot go further than 160. That's your design value for the stress, okay? And in that case, you calculate the thickness. So you have something like this, okay? And you will see that this expression is quite similar to the one that it is employed by the classification societies. Okay, we have A, that's the shortest dimension, P, square root of P, that's the pressure, and this square root of sigma, which is the allowable stress. And then here, we have a constant which depends on beta. And beta, you see that this is this one here, but depends on the aspect ratio of the plate. So it's quite similar, believe me. Okay, now, if we go on, this is the expression that classification society use. Let me go back here. A square root of P square root of sigma. A square root of P square root of sigma. And in the front, you have a constant which depends on the aspect ratio. S over L, that's the aspect ratio. In our case, we have the square root of 6 beta. So it's basically the same, okay? Now here, they include a TK. Okay, and this TK, it's a corrosion allowance. Okay, we have to accept that you calculate a certain thickness, 8 millimeters. That is enough so that if you apply certain pressure, the stress level will be below the acceptable value. Fine, everything was corrected. The problem is that after 3, 4, 5, 6 months, the corrosion will reduce the thickness. So you have the same load, less thickness. That means that the stress will be above the allowable value. What can we do? What we can do is when we build the ship, okay, we calculate the thickness to sustain the load. And then we add what we call a corrosion allowance. So that means that it's a piece of the thickness that you can accept it can corrode. After 3, 4 years, this corrosion allowance has vanished, you are to go back to the first part of the formula. But you cannot allow this thickness to reduce more. What do you have to do? Change the plate and go back to the original thickness. Because if you reduce the thickness more than this, that represents a hazard. That means that if you apply the P, the stress will be above the allowable value, and you cannot allow that in your structure. Okay? I'm attaching this because it's very interesting, okay? You see that they have this expression, allowance, but this expression depends basically on the size of the ship. They are not telling us about the spacing. They are not telling us about the pressure. So what I think is that this is the design thickness considering the operation of the ship. And this other formula is the thickness that you require for the plate considering another situation. For example, when the ship sits on the dock, the pressure is because there is a block where the ship sits. So the force exerted is different than the one that you have when you are floating. So you have to consider both situations, okay? Let me connect because my battery is going. What's wrong with this? Okay, I'm sorry about this. Okay, so you have to consider both situations. That's why you have these two types of formula. The one that we recognize is basically plating, supporting pressure, and you select the thickness so that the stress is kept below a certain value. And the other one is the special situation that we have to think, and the thickness has to consider both situations. So you calculate the two values and take the larger. Okay? So that's that. In the bottom, see, this is something which is very interesting, okay? How do we select the value of sigma? And you see here, there is a difference between transverse stiffening and longitudinal stiffening, okay? And you see that when this is transverse stiffening, this value here, remember, TB is as it was built, and R is the required. Let's suppose that in your ship, your hull has exactly the amount of section modulus, exactly the one that you need, required by the rules. So this ratio is 1. In that case, you can see that the allowable stress is going to be 60 megapascals. And in longitudinal case, okay, it's going to be 120. Why is that? Okay, we have to remember these things you have to have in your mind, okay? system, okay? The transverse elements are closer than the longitudinal elements. Okay, and in that case, remember that the largest bending moment is aligned in the direction of the shortest side. Okay, so in this case, we're gonna have that the bending moment in this direction, okay, is larger than the bending moment in this direction. So if this is X, this bending moment will generate a sigma X, very important. This is the tertiary. And in this direction, in the X direction, you're gonna have also the primary stress. So the two are going to combine directly. And that's why you have to think of that. So that means that you can allow the tertiary stress in the transverse framing system with a less value than in the case of the longitudinal framing. Okay, it's something which is very interesting. Okay, people? Any questions about this? Any questions about this, people? Any questions so far? I can erase some of this. Oh, shoot. What is it, man? Okay. Any questions about this, people? Any questions about this? Okay, so we
What
can
happens
proceed.
if the stiffness are parallel to the girders? How we could
But
consider
in that case, the sigma y, we're going to do an example on that. The sigma y, not sigma x, sigma y is going to be more important in the tertiary case. But you have longitudinal, that's x. Transverse, that's y. If this is very large, it's not going to be added directly to sigma x because they are orthogonal. In this case, the tertiary stress is going to act in the x direction. And in the same direction acts the primary stress. So the two combine directly. That's why the allowable stress for the tertiary case, that's what we are discussing here, from classification rules, has to be reduced. Okay? So let's go on with this. Here we have this is a plating. I'm going to discuss about the boundary conditions that we mentioned before, okay? Here we have this model, okay? This model of a plating plus some stiffness in one girder, okay? And this is the normal stress, and the normal stress, this is at the top of the plate, and this is at the bottom. And you see here that this color, okay, more or less is going to be about here. So that's positive. That means that on this side, this part here, the stress is going to be in this direction, in the x direction, it's going to be positive. But then here you have the reinforcement, the stiffener. You see that this is blue. So in blue, you have negative sign. So you go positive, negative, positive, negative, positive, negative. So it's like seeing a group of clamped plates, and you accept that in a clamped plate, on the border, you have one sign of the stress, then the bending moment changes in the center part of the plate. Okay, so in the top of the plate, the stress goes from, in this case, from negative to positive. And then you go back to positive. Negative, positive, negative, positive, negative, as you go in each one of these plates. So it give you an impression that it's like having a group of clamped plates, okay, one on the side of each other. But now in the lower figure, It is the same, but we're looking at sigma x, but in the bottom face of the plate. See, on the top and on the bottom. The thickness is the distance between this and that faces. Okay, in the bottom, remember this is bending. So you have the opposite sign for the stresses. So here, for example, in the central part of the plate, okay, this was positive. And you see here, this is blue, this is negative. Okay, so you have the plate bends on the top, compression, on the bottom, tension. And then you move on the plate and you have something like that. On the top, it's going to be positive, and the bottom is going to be negative. Okay, so in each one of these panels, you could see some resemblance from the clamped plate, but it's not quite. This is something that I emphasized in chapter 4. It was that if you consider a completely clamped plate, okay, the stresses on the side, okay, in this direction, are more or less double the stress at the central part. So you got a certain value, positive or negative. Here, you have the opposite sign in about half of that. And then you go back to the other side and you recuperate the same value that you had before. Okay. Something like that you see here. You go from positive, negative on the center, and then you go back to positive on the other side. But the relationship of the values are not twice. Why not? Because we have to accept that this plate panel is not fixed, it's not clamped, because both ends, they have to move. And also there is some rotation of the stiffness. So that prevents from considering these panels as they were clamped. Okay? Now, let's see some detail of that before we break this class. Okay? Let's consider that we have to select the thickness of a plate. Okay? We are going to apply a pressure of 80.4, okay, kilonewtons per meter squared. The allowable stress is 120 megapascals, and the spacing between the smaller side is 60 centimeters. That's about this. Okay, so what do? Let's suppose that we change the other dimension. So we consider different values for the L dimension. And this is the result. Okay, so here I have different values for L. We start at 0.6, so it's equal to that. So in this case, the first line corresponds to a squared plate. Okay, here what I did is I applied the formulation from DNV. Okay, that's formulation here. I didn't include the corrosion allowance. I have the sigma, I have the pressure, I have S, and K depends on the ratio S over L. Okay, so changing L will change the aspect ratio, and according to that, will change this constant taken from DNV regulations. And from that, I can select the thickness applying DNV formulation. Okay? Then I look it up in Timoshenko's book. So I could calculate, or I could take the values for beta on the side and at the center. Okay? So this is what I'm looking right now. So this is what we're doing. So I'm taking this plate and I'm looking at the bend moment here and in the central part. Remember that the central part is basically half of this value. I'm not going to consider the sign because we know that at the central part, of the plate, the sign of the bending moment is the opposite as in the one on the side. So I take this value, that value, and with this, we could calculate the bending moment. With the bending moment and the allowable value of sigma, we could calculate the thickness. So this is the thickness that we will require considering the bending moment on the side. And this is the thickness that we will require considering the bending moment at the central part. In graphical way, this is what we have. If we consider this plate as clamped, completely clamped, and we take the values on the side, we will require this value of thickness. If we consider the formulation from DMB, this is the result. And here, the other curve in green, thickness that we will require if we consider the bending moment in the central point of the plate. And my analysis is that when you have equations, we cannot consider that the two sides or the four sides of the plate are clamped, because both stiffeners, they deflect and they rotate. Especially they rotate. When they rotate, the slope is not zero anymore. So that produces a redistribution of bending moment. And the result of that is more or less that the bending moment in the central part of the plate and on the side basically are the same. And that's what we're seeing in this figure. So as a general rule, we could consider the plate as clamped, but because of this redistribution, the reference value will be the value at the center, not on the side. So that will provide a good approximation of the maximum stress in the plate. When you have these reinforced plate panels, you cannot consider that as all clamped plate. Makes some sense. Okay. Okay, people, that's it for today. Today is Friday. I hope with the explanation I just presented, you can go on with the assignment. Tomorrow is Saturday, okay? At 10 a.m. tomorrow, I will be available in my Zoom session because the students from the ship dynamics, they are also working a homework, and I'm going to be available for them. So if you have any questions about this assignment, and do you think I can help you? Yeah, you can. You may come tomorrow, okay, at about 10 a.m. Okay, and after that, yes, hopefully I can answer your concerns, your issues, your questions about the assignment, and you will be able to complete it. Okay, so if somebody wants to come tomorrow at 10 a.m., yeah, I'll be available to try to help you out. Okay. Is there any final comment, any final question, people? Any final before we break up? No? Okay, then have a nice weekend, and I'll see you Tuesday. Next week, we have the Naval Engineering Student Clinical Sessions on Wednesday. Okay, we're going to start at 7:30. So it could be a good idea if you may come, because in this session, we're going to have an in-person technical sessions, okay? We're going to go back to our previous, our original methodology, okay? In the auditorium, 7:30 until 9:30 and all of that. So it's going to be a good idea for you to come, and we can finally meet each other, because unfortunately, I still do not recognize some of you. Okay, so make a plan So you can come next Wednesday and we can, yeah, I can invite you to a coffee and donuts, not donuts, but at least rosquita. Okay, in that case, if there's no more questions, then I'll see you Tuesday.